right, everybody. Welcome to today's developer meetup event. We're happy to have you. I'm Gabe Perugine, and I'm our community leader, and I'm pleased to have our panelists today, Guido Hoffman, Antoine, and Erwan. They're on the TechSoft 3D side, and we also have Raphael from Autoform joining us today. And today we will be talking about custom shaders. Before we get started, I do have a few housekeeping items to go over. This event will be recorded and made available at the end. I'll give you guys a link to where that will be. Secondly, if you want to ask questions, please feel free to and put them in the Q&A panel, and we'll get to those at the end. And also, if you could just introduce yourselves in the chat and where you're from, I'd love to see where everybody's coming from. So without any further ado, I'll hand things over to Guido, who will be getting us kicked off. Guido, over to you.
Okay, here we go. So let me just quickly share my screen. The usual process here. Okay, let me know if everybody can see the slide. Okay, so we're going to talk a little bit about the HPS custom shader. So to start off, I'm technical fellow at TechSoft. I'm with the company for over 20 years, mostly on the visualization side. And I'm not doing that much more development anymore these days, but I did make these initial demo videos for the shaders, and that's an area that I'm somewhat familiar with. But on the deeper technical question, I'm also backed up again by Antoine and Erwan, who are both developers on the Visualize team, who had a big hand, I think, in developing that the shader functionality. So they will be able to ask any deeper technical questions. So let's get into it here. So quick overview. I'm not going to have too much slides. It's going to be mostly practical stuff, but I'm going to give a quick introduction over the shader stuff in Visualize. And then again, I'm going to have 4 different examples that I'm going to run through and show a little bit of code and demo in the MFC sandbox. So shader basics in HPS. So we support Vertex and Pixel shaders. You can write your shader, and I'm assuming you have a little bit of. I'm not going to start from the very beginning of what shaders are, and so I'm assuming a little bit of familiarity in general. So I'm not so, but again, you can ask questions later on if something sounds a little bit unfamiliar. But so Pixel and Vertex shader support in HPS. You can write your shader essentially in GLSL and HLSL, actually that's a typo, which is basically Windows and Linux, or OpenGL and DirectX. But we have also a common macros that make it easy to write a shader that runs on both systems. So internally, we're going to compile those shaders to GLSL or HLSL, but then you can write your shader in a more abstract way that runs on all those platforms. But it's important to keep in mind, especially if you have a shader coming from another system, or you want to convert a shader from a different source. You can apply a shader to either triangles, lines, or points in HPS. That is not really directly mapping to geometry. I'm talking about this later. And a shader is essentially like any other, treated like any other attribute. So it gets inherited down the tree. You can override it. All those things you can do on materials, visibility, or any of these other standard HPS attribute also applies to shaders. Very quickly, and again, we dive into the code, but here's a basic workflow just to have a quick overview. So first thing is you write your shader, of course, that's not mentioned here. Then that shader source, which is essentially just a text, the ASCII text file, you pass it in with using the set source function. Then you define the inputs to the shader. I'm going to talk a little bit more about that in the demos, but basically there's a bunch of standard inputs, standard parameters or structures that are always available to a shader. But then there's some that you have to specifically request, like for example, the normal in the Vertex shader. And that's what you would set with the set inputs function. Then you define additional outputs that's specific to the Vertex shader. So as you can pass essentially data from the Vertex shader to the Pixel shader, and that's what you do with this function function here. And then optionally, you can also define essentially a bunch of uniforms. That is extra data you essentially inject into a shader from your main HPS source code, and that's also what you define here. So then if you have all that done, you define the actual shader. It gets a key, and then you set that shader on a particular segment with either the vertex or the pixel shader function. And then also optionally, you can set the actual data for the pixel shader, so the actual values in these uniforms. And then at the end, if you run into an error, I'm going to show you that a little bit later as well. You will use the standard HPS error handling mechanism to at least get some information. Debugging a shader is a little bit tedious and tricky. There's no breakpoints that you can set, but at least you can get some information if something goes wrong, and then go from there. Okay, quick about limitations. So Vertex Pixel shaders, there's no geometry shaders. We don't support that. I'm not sure if that's on the roadmap. Probably not. I think it just maybe doesn't fit with hoops or HPS, which is quite a complex system. There's no render to texture yet, and no additional passes. So you're really confined to writing either your pixel or vertex shader that fits into our existing pipeline, essentially. So again, it would be probably tricky for us to support that. I'm not sure. That maybe the developers can talk about that later. We have limited ability to modify the lighting. So because all that is the lighting calculations already done and before the shader is executed in the pipeline. But of course you can calculate your lighting from scratch in the shader. It can get quite complex, but yeah, you have limited access to that. And there's no guaranteed mapping between Hoop's geometry and the shaders. That means obviously Hoop support a lot of different geometries like lines and text and different other entities that can have very complex attributes attached to them. They could be rendered in quick moves geometry, or maybe the line has some pattern attached to it, or text sometimes it's rendered as lines or as faces. So it's not really guaranteed what shader is actually going to be executed and how the shader behave, what the input will be. That's something that a little bit of you have to do with trial and error, because HPS is just a complex beast which supports a lot of different things, sort of use cases, different attributes, and they all interact with each other. And so you really have to keep that in mind. Okay, so now without further ado, we're gonna start with the examples, and I'm give a quick overview of the first example here, which is just a simple pixel shader that just does some screen space calculation. It's actually a kind of cool looking shader that I've converted from Shader Toy. It's I think a very simple like signed distance field calculation to create some like cool looking blobs, but it's really just an example of that you can take any shader and really convert it to our system fairly easily, because again, using our macros there. And that shader uses 3 uniforms that are passed into it. One is simply a counter, because something is actually moving on the screen, so it needs to have some kind of like thing to update, and then it also passes the screen resolution into the shader directly using the uniforms. So I'm going to switch now to Visual Studio. Okay, and here we have that initial shader code. I'm going to just quickly go through it and maybe ignore the first part. So here you see you can actually set and unset a shader again, just like any other HPS attribute. But just to give you a quick overview of the steps here, again, you read the shader. This is a simple helper function that reads the shader from a text file. The actual shader is here on the right. Again, I'm not going to go into too many details on the implementation, which I'm not even quite understand in all its details. But it's just a simple image-based shader set that has these signed distance fields to create some blobs. Not too complicated, but it does take a bunch of these uniforms here to pass the data through. So define the shader, as I mentioned in the initial slide. You define the pixel shader here. You define the uniforms that you want to pass through. In this case, that you can either, in general, there's a few restrictions on how this data is organized, but in this case, we just need a float for I think, if correct me if I'm wrong, Irvin or Antoine, you can't actually pass a single value as a uniform. It always has to be either like an XYZ, like a positional value essentially, or like or a matrix, float 3 or float 4. But we're passing the uniforms here. We're defining the actual shader in the next line, and then here's just some code because we actually need to create a selection here. But the relevant stuff continues here. So here we're basically setting the uniform data for the shader. We're starting off with like setting this timer value to 0, and we're also passing in the in this case hard-coded the resolution of the screen, and then again we define the uniform data as well as the pixel shader itself on this segment here. That's our current selection. And then at the end, we're setting this value here. And then we also set a timer because we're actually iterating over these things here. And you can actually see the timer function up here as well, which really does nothing than increment a value, and that gets passed on to the shader every couple of milliseconds. I'm going to run this code here. And this is, by the way, this is the MFC sandbox. So really just a basic sandbox with this extra shader code implemented in every most Visualize developer are probably going to be familiar with that. So I'm going to start with a simple example here, load one of our like standard sample models, this case a BNC. And now I'm selecting something, any part of the model here, and that's where that shader gets applied. And then I have that in the user code here. And you can see that shader, again, an image-based shader running and using essentially this timer variable to increment its value and create some pretty cool effect. We can have this other, if you toggle that, the shader gets turned off again on that segment. And to see, I can also apply this now to the, now it was only applied to this one shell, but I just go open the segment browser here and now select top level segment. I can apply that shader to the whole model. So again, these shaders follow the same principle as any other attributes in Hoops Visualize and get inherited down the tree. And that's also true for that uniform data as well. So you can have a top level shader that has a certain uniform, and then some of the shader below can have a different value, just like color or any other thing. Okay, so that is shader versus shader number 1. Okay, let me go back quickly to the slides here and go to the example number 2. So this is a slightly more complex shader that is actually two shaders. First, the vertex shader, where that is very simply takes a position and the normal of a vertex and passes that through to the pixel shader, and automatically gets interpolated. And then it's available in the pixel shader to actually map some, in this case, a simple like checkerboard pattern that is dependent on the pixel shader information on the object. So let me maybe just go through the code and explain it there. So for shader number 2, again, it's the same. It follows the same pattern. We first start with reading the shader file. We are in this case a pixel shader. We just define it. There's no other value that we need to add there. And then on the vertex shader side, we request the normal. We need that. That gets passed through to the pixel shader. So it's not one of the default parameters that are already available in the shader automatically. So we need to request it with the set inputs here. Then we also want to pass through 2 values, the position and the normal, from the vertex shader to the pixel shader. So we need to add those as well. We need to set out by adding them here to the set outputs value. And then we define the shader. And in this case, we are applying the shader to the top level model segment. So it gets applied essentially to the whole model, not just a single mesh. And because we have a vertex and a pixel shader, we need to define both. And we apply these, and I didn't mention that before. Here you have the ability to say if you want to apply those to lines or triangles or points. In this case, we just want to have them apply to the triangles. So again, if I run this code here, and in this case, load a different model, which is like the skeleton head. 1 second to load, it's a little more complex. and just running this, applying the shader now. And you see that creates this kind of semi-correct checkerboard pattern based on the vertex and normal input. So it's not camera dependent. Oops, I think let me go back to the orbit here. So you see, it's basically like it operates like a texture, and it in fact uses its own lighting calculation here as well, which just a simple directional lighting. That's all kind of done in the pixel shader itself. Okay, let me see. Looking on time, and so these, but that's basically just a pixel shader that uses a vertex, some information from the individual vertex, say that interpolated information as input. Okay, let's go back to the PowerPoint here, and now let's go to example 3 and 4, which are kind of very similar. So I kind of group them here together. These are just vertex shaders that actually change the position of each individual vertex, which is kind of nice in this case to create like a simple wave effect or like a morphing effect. And we apply that in this case to triangles and lines. One caveat here, if you make changes to the vertices, of course, then then that might lead to the fact that picking is not working correctly anymore, because picking in communicator, in visualize is in a lot of cases or mostly analytic. So you might be HPS might not know where the object actually is. So you might have to write your custom code there. So let's go quickly to the source here for this one as well. Shader code 3. We're switching this to wireframe here. That's not relevant, just to we get the lines as well. The faces are already highlighted. Then same principle here. We read the shader. We apply the shader. In this case, again, we have this one uniform, which is again, it's a counter because we have that wave is actually animating. And then we're just gonna define the vertex shader and apply it to the whole model. And in this case, again, we're applying it to the lines as well as the triangles. And that's also true for the uniform data as well. And then we have that timer here. Take a quick look at it again. See what it does. It's very simple. It just basically increments the timer and then applies that uniform data and performs an update, so we get an animation. So if you run that code, in this case, we load a simple model here and apply the code, you create that wave effect. And that's actually, it looked like a simple face, but it is actually highly tessellated. So we're not actually creating any vertices in the shader. So if those have to already exist. So in order to get that wave effect, you are basically just manipulating the position of these vertices in the shader. And we have another shader. Let me run the fourth one, just which is very similar, which has another effect here. That simply takes vertices and turns them into kind of a semi-sphere. You see that here as well. It works essentially the same way. And the shader itself, you can look at that quickly here. The wave shader, it's very simple, just a simple sinus curve that gets that based on the position. So it's a little bit offset for each vertex. Very straightforward, and the same thing with that other shader. One thing important to mention, and I maybe should have that in the slide as well, is this function fully transform. So if you change the vertex in the vertex shader, you still need to project it in order to get the correct result. So that's what's happening in this fully transform function here. You basically take it from the object space into the camera space with this transform matrix by performing like using the model view matrix and the projection matrix that is available in the shader to transform the point, and then otherwise it would not be at the correct position, not right. Okay, well, I think that's it. We are 7:20, almost close to the line. Antoine and Irvin, do you have any other things, any other insights, or anything I've missed? Again, this is just a very basic introduction here to shaders. There's a lot more going on, and shaders can have all kind of complexities. Maybe a quick look at the documentation makes sense. So I'm going to quickly point out here. So if you want to see what data is actually accessible in the various shaders, you can take a look at it here. I mentioned that before. Some of that you need to request. Others is available only in some cases if there's textures on a model or not. So all that information is available here in the documentation. And maybe a very quick tangent on debugging. As I said, if your the HBS has an error mechanism, and if there's any error in the shader, you can basically get that. So I'm gonna maybe do that here for 1 second. If I put like a typo in here into this wave shader, and if I then run it again, give me 1 second here. You see, it basically you get an assert, and then using the HBS event handler, you also get an error, and that actually gets put out put into the console here, at least in debug mode. I'm not sure if you can see it. This text is a little small, but you get essentially an error message back that it gives you some clue of what went wrong. In this case, it says we output X is an invalid subscript. So that should tell you immediately, hey, there's something wrong with my shader code, and just in general, let you know what went wrong. Okay, well, any other insights? Or should we move on to
I want to move on to Raphael, but Jonathan did ask in the chat if we were going to share the code publicly. Is that possible to post it in the form?
Yes, actually, that's a good point. I haven't done that yet, but that is something we can certainly do. Let me get in fact, I can zip it up, and in the next couple of minutes, I will have that as a link in the forum.
Thank you, Guido. So while he's doing that, I will go ahead and switch it over to Raphael. Raphael is from Autoform, and he's going to share how he's using the custom shaders. Raphael, let me know if you can share your screen, but I'll hand it back over to you.
I can't share my screen so far.
Okay, let's see. Okay, you should be able to now.
Yes.
Perfect.
Let me know when you can see it.
I can see it. You're good to go.
Okay, perfect. So thanks for the introduction. I'm Raphael from Autoform. We work on software solutions for simulating sheet metal forming and assembly, mostly in the automotive industry. And I believe we were one of the main drivers for the support of custom shaders and hoops. So yeah, I can give you a bit of a demo what we use shaders for and why we wanted them initially, what were the limits before. Yeah, so first of all, a bit maybe surprisingly, the demand for shaders was mostly because of the limits of F-index colorings. So most of our shaders are conceptually quite simple, but very hard to implement, sometimes impossible to implement in F-index colorings. However, again, pretty simple to implement in shaders. So the first two limitations for our first kind of use case were these two. First of all, you can't, or you can only interpolate linearly for F-index colorings. So of course you can transform your data point with some nonlinear function f to obtain some F-index and then put that onto your shell vertices. However, then you have the linear combination of some non-linear function applications instead of some linear combination. So it's only an approximation, basically. Secondly, you can only put scalar data on f-indices. There's no option to use vector data. So I can show you what we use this in our software for. So basically here you see some plots of minor versus major curvature. So you see either that it has no curvature or only single curvature or both curvatures, and whether they are convex or concave. In particular, you can see very quickly whether something is spherical or cylindrical or flat or something like that. And this is like curvature is nonlinear, and it's minor and major curvature. So it's two-dimensional data, and you can see that it interpolates very nicely, very smoothly. Also, this is not because of some nice triangulation. You see that the color doesn't necessarily follow the triangulation boundaries or anything like that. Exactly, and yeah, with shaders, it's not too complicated to do that. Our second use case is just continuously interpolate data on a shell. So imagine you have a color map from green over yellow to red, and green corresponds to a data value of 0, red to 100. You use f-indices 0, 1, and 2. Not too complicated so far. And as long as your data on the shell is really within that range between 0 and 100, there's no problem. However, as soon as you go outside of that range, things get quite complicated. So, for example, here on the top vertex, you have a data value of 1000. And if you would just apply f-index 2 to that vertex, so everything above 100 would get f-index 2, then you would directly interpolate between red, yellow, and green from top to bottom. However, what you actually want is everything above that red line should be red, and only below the red line you want to interpolate red, yellow, green. I can actually show you the old state using f-indices in our software. So here again you have some mapping. Let me zoom in on one triangle and label that. So this goes from 6 to somewhere, yeah, roughly 10. And now you see within that triangle, the complete color map is used. However, if I change that now to something smaller, let's say 7, then it stays the same, because the largest value here just gets, it's above the color scale, so it just gets the largest f-index. The lowest value is below the color scale, so it just gets the lowest value. Nothing changed in respect to f-indices. So it's still the same coloring, but actually we want, like, until somewhere here, it should be green, and only then we want to interpolate. I can show you the new state using shaders quickly. So same thing, and we zoom in on some triangle. And we label that. So it goes from 0.2 to 0.5. The complete color scale is used, as you can see, and if we decrease that to 0.3, then actually we obtain what we want, and we only transition at 0.3 to, yeah, interpolating colors really exactly. Of course, here in this little example, you have a lot of F indices spare. I think we can go up to like something 65,000 or something like that. But as soon as you exceed this range, or like in particular, if you have some non-finite color range, then this is really kind of a problem. Or if you just don't know what your values on the shell are in like before you want to show this color scale. The next use case is mixing discrete and continuous colorings. For F indices, this is exclusive per shell, so you can't mix that up. And I think we have kind of a nice use case for that, actually. Let me quickly show you. So first of all, so actually there are multiple. First of all, here you see these black areas. This is some area where we don't have any values. So of course we could just interpolate to black, but that would be kind of strange. In particular, if it would be green around it, then there would be some transitioning phase and you wouldn't know is at that place still a value or not. So this way it's much nicer, but further we have some special color maps. Here the user can predefine some specification, some range of values that he expects his data to be in. In this case, it would be 0.5 to 1.5, and everything in that range would be grayed out, and only things outside of this range are colored according to the color scale. So in particular, the user can very easily and nicely see, okay, there are values that I need to take care of. There are values that are outside of what I expect. And for this, it's really, really nice because these color transitions between like continuous interpolation and discrete interpolation really boil down to a simple if statement in the shader, in contrast to really cutting the mesh if you want to use F indices. And we have kind of the complementary color scale as well. So here everything within these values 5 and 0 is colored continuously, and everything outside is black or white. So if I change that slightly, then you see like in these areas we have values that are below 0.1. Yeah. So that's it for this use case. Another one, again, very similar. Assume you have continuous data. You want a discrete visualization of that. Let's say we have categories A and B, A ranging from 0 to 1, B ranging from 1 to 5. So they have different sizes. Then for using F indices, you would need the color map that actually kind of resembles the same ratio as your category sizes. So you would need to duplicate your red color multiple times. So you would enlarge your color map. And in particular, like if you have arbitrary floating point numbers as your range, then it might get quite complicated to resemble that ratio. And even worse, if you just want to color everything above 1 to infinity with some color, then I think there's no sensible mapping for that. So again, the shaders, that's basically only a few if statements, same data, nothing on the shell actually changed in terms of data. We don't need to insert new F indices or anything like that. But we have a discrete representation from -infinity to 0.1, and then from 0.1 to 1, and all the way up to infinity. And I think that is very handy for our customers, because again, it's very easy to see whether he needs to take some action. He can directly see, okay, this is some region I don't need to care about. This is something I might need to be concerned about, and this is not acceptable. I need to take some action. Yeah, so I think the use case is very natural, and I expect a lot of you have kind of similar use cases for that. Yeah. So these were basically the things that concern f-index like colorings. And as I said, these were like the main reason why we wanted to have these shaders. But we also have some shaders that are not concerned with some coloring of data, but just use some shading, basically, some special lighting. And these are zebra lines and wrinkles highlighting. So I can show you that as well. Here, these are the so-called zebra lines. Basically, it's a simulation of a light tunnel. So imagine you have like around this part a lot of long stripes of light, and this way, if the part reflects these stripes, then you can easily see curvature changes, and therefore it's rather easy to see surface defects. Also, you can like fix these lines, rotate around, zoom in on it if it's some configuration of particular interest. And the second example is this one. So now you don't see any kind of shader, it's just our usual rendering of our simulation output. So here you see some sheet metal, and in this way it's really hard to see some surface defects. It looks all very smooth. And I think for general depiction of CAD data, that's typically what you want, that everything is illuminated quite evenly and nicely. However, in this case, it's very helpful to kind of take contrast to the extreme and specular lighting a bit to the extreme. And very easily you can see that there are a lot of wrinkles around this part. Again, you can fix that if you want and rotate around like this and examine it in further detail. And for that reason, it's very helpful because we can basically completely override the default shader of hoops. So that's it for my demonstration, basically. I can also tell you a bit about like our experience using shaders and some insights into development. So to be very honest, like most of these f-index colorings we already had before, so without using shaders, but there we actually cut the mesh. And of course, that was like an extremely large workaround. It was complex to implement and hard to maintain. We made that work, but still it was a lot of effort. In contrast, all our shaders have, I think, less than 100 lines of code. So they are really simple, nothing too complex. So in that regard, it's really valuable to us. And I think that's really the main reason to use them, at least in our perspective. Also, in terms of performance, like if I compare these f-index colorings and these shaders, then what is costly is compiling the shader. And if you, I don't know, just change the value here of the color map, compile the shader once for this change of the color map, then it's really fast. Of course, in contrast to actually cutting the mesh, it's very fast, it's much faster. In the case where you need to put new f indices onto your shell, again, it's faster to compile the shader. If you don't need to do anything of that, then it's pretty much comparable. So in particular, I measured a bit how much time that needs for us reading a file, replacing some text tokens, and then compiling that in hoops takes about 0.1 to 0.5 milliseconds. So really not a problem if you do that once per change of the color scale or anything like that. However, it might be a problem if you do it once per patch or something like that. Like CAD geometry typically has like a lot of patches. If you have somewhere in the range between 1,000 and 100,000 patches, that might take quite some time, somewhere in the seconds, and users probably will notice that. And even worse, you waste a lot of GPU memory. So it's, in my perspective, it's really important that you insert the shader only once and then apply it to as many shells as you want. But it really helps like to have some kind of central instance that you can ask, that you can request the shader of, and if it already exists, it just gives the already compiled shader back, like the keys of it, and otherwise, and only otherwise, it compiles it. And then if you compile it only once, it's really fast to use and really creates some great value. Yeah, I think that's it from my side. I hope you enjoyed it. I hope you're a bit excited about shaders and try it yourself. Maybe you got a bit inspired by all these variants of color scales. Yeah, let me know if you have any further questions.
Thanks so much, Raphael. Those were some great examples, and it was a very practical use of the shaders. I do actually have one question from James here in the chat. He asked, how do you access your custom vertex shader from within the shader?
Yeah, so maybe I can just quickly, I mean, by the way, I posted all the demos, including the source code for the shaders. You see that in the chat, so you can just download that package. And it should be fairly straightforward to get things up and running. I can maybe quickly, and I think you're talking about the uniform data, how you would access that in the shader. So maybe just maybe quickly get back to the, share my screen again here. So you see on the right, this is one of those vertex shaders I used. In this case, this wave shader. And if you look, and that's a shader code. And you see the uniform data is passed through in this structure called uniform user vertex. And so underneath there, you basically find your previously defined uniforms, which you have, in my case, I've given that the name counter. And if you just go back to my shader code here, it's in the example number 3, you see I added this uniform here, called it counter. It's a float 4, and added that to the Pixel Vertex shader kit. Oh, I give it the wrong name actually, but it's a Vertex shader, and then that becomes accessible then in the shader itself with whatever name you defined it as. Hope that answers your question.
Cool, cool, cool. Well, I don't see any other questions in the chat, but if anybody does have them, please post them there, or you can raise your hand and I'll unmute you. But I did also want to share the link for where our recording will be posted. It'll be posted in the form. So if you guys haven't created an account there, please do. It's where you can get all your news information. Guido posts a lot of kid code snippets there, so it's a great resource, even if not for this recording. Let's see, do we have any other questions? Guido, did you want to answer the last remaining question in the chat or no? You marked it
Uh,
as to answer.
which one is that?
Sam's last question.
Oh, there's a yes. That question is very very specific to your customer from through spatial. So I don't really think we have any specific insights. Maybe it might be good, Antoine and everyone, if you have any information of, is there any more work done on the shader support? Certainly bug fixes are always part of it. I would imagine that's always going to be important for us. But is there any other new features planned or anything you can maybe talk about, or is there like a general roadmap for improving the shader support in 3ds and HPS? Can you speak to that maybe?
I don't know if there is some new information. I can add something for the debugging part.
Yeah.
Guido showed us the HPS part. On the 3ds side, we have an additional functionality. You can use HC compile shader, and so you can compile your shader and test it, and then get the error if there is some error. And it's easier to use because you have the entire shader program, and you know the line where there is an error if there is one. So I can add that.
Maybe that may be interesting, Raphael. So you wrote a bunch of shaders with 3DF. How is that? What is your workflow with regard to development? Do you have like a special editor which does syntax highlighting on the shader? Obviously, you can't really or do you have a way to even step into a shader directly, or is it also what I said is a kind of trial and error from that
Basically, what you said, like we can't step into it. We just trial and error, compile it, see whether it throws some error, and then correct that line. So that is a bit tedious, but as I said, most of these examples are really short. So in the end, it's not too much effort.
All right. It doesn't look like we have any more questions in the chat right now. But if anybody does have any follow-up questions, again, the forum is a great place to ask those questions.
Maybe one more thing. I want
Okay.
so again, I came from this a little bit as someone who hasn't worked with shaders. It's a new functionality. It's something that I think we obviously going to improve on and add things to it. And there might be issues. There might be certain like workflows that are not perfectly supported. I think we're always very responsive, and so we are definitely. I mean, it's really get your. I mean, everybody in here just get started using shaders. And come up with some. There's so many things you can do with it, and also shoot yourself in the foot, I guess, because HPS is a complex system, and it has a certain way of working, and if you make changes in the pipeline, it's a little tricky. But I think the best way to kind of to just kind of put some try to use it and see if something goes wrong, or you're specifically missing some of the data that you expect in the shader. And I went into that in a couple of cases, but usually you can just pass this in through these uniforms. But in some cases, things might not be obvious. So we are obviously techs are very responsive and willing to help anybody who's using that shader stuff.
All right. Thanks, Guido. Thanks, Antoine. Thanks, Erwin. Thanks, Raphael. Everyone did a great job today. And thanks for sharing such valuable information. We will have another one of these later on, I believe, in 2 months, 2 or 3 months will be the next Hoops Visualize meetup. There will be a survey at the end of this on topics you might want to hear about or things you want to discuss. Please be sure to fill that out just so next time we can deliver content that's more relevant to you. Again, thanks everyone for joining, and we will see you again next time.